Welcome to practice number 151. Today we're looking at something I never thought we'd see. It's so bizarre. I'm just going to tell you what it is. Superhydrophobic foils. So if you don't know what that means, the term hydrophobic, it's quite easy to break down and understand. So the first part is hydro, which means water, and the second part is phobic, which refers to fear. So putting these two together means it's a surface that repels water, or at least does its best to do so, hydrophobic. What that looks like is that when you pour water onto a surface, so for example, a lot of modern day rain jackets, if you were to pour water onto them, instead of it just pooling and going everywhere, it starts to bead, and as soon as you start to tilt the surface even a little bit, the water just runs off very easily. So the opposite to this is hydrophilic. And a hydrophilic surface is one that loves water, and that's what the term means. So again, we have hydro, which means water, but this time we have the term philic, which means love. For example, the term philosophy is comprised of two words, philo, and which means love, and then sophia, which means knowledge, so the love of knowledge. Likewise, hydrophilic surfaces means that the surface loves water, and when you pour water onto the surface, it spreads so easily, and the entire surface gets wet very easily, the opposite of hydrophobic. Now, the term superhydrophobic refers to surfaces that are extremely hydrophobic, so the best of the best at repelling water and reducing how much of the surface gets wet. And this podcast is about a superhydrophobic hydrofoil. So you have this wing in the water that repels water. So how does that even make sense? Well, we're about to find out. So these researchers of this paper, as I'll scroll up and I'll tell you which paper it is. It's numerical study on drag reduction and weight modification for the flows over a hydrofoil in the presence of surface heterogeneity. And you can find this in the link in the description. So if you're into aerodynamics or hydrodynamics, the concept of changing the lift and drag of a foil to help you achieve whatever you want to is a standard idea. We do it all the time. But this approach of using a superhydrophobic surface is so novel and it's really out of the box. We always try to use different geometries, change things a little bit, mixing fast moving fluid into the boundary layer, or putting more than one foil in the geometry or something similar to achieve this lift or drag reduction. But this study looks at solving the problem in a very unique point of view. It looks at changing the surface to achieve our goals. But does this concept even make sense? Is there any theory that would indicate that this idea is even worth looking into? Well, it turns out that it does make quite a lot of sense from a theoretical point of view. So the surface of an object is what the fluid, whether this is air or water, is touching the surface, and that's what affects the fluid's behavior so much. In fact, this is where most of the vorticity is created for most flows. The theorem is that vorticity can only really be created there at the surface. So the surface greatly affects how vortices are created and how they roll up and how they are shed. The surface also affects the boundary layer growth in general. We know, for example, that a rougher surface will create a more turbulent boundary layer, which will greatly affect at what angle the flow will separate and hence stall. The surface is so important at altering how it interacts with the water, that in this case, making it hydrophobic has the great potential of altering the flow physics and hence the lift and drag coefficients that are produced. So this is a very out-of-the-box approach that is heavily supported by theory and not just some harebrained idea. There's a lot of potential to it. But how much it can affect the flow physics and resulting forces is unknown, which is exactly what we'll go through in this podcast. How does hydrophobic surfaces work? So the authors explain it as high aspect ratio micro or nano high aspect ratio micro or nano topography combined with low surface energy, resulting in super water repellent surfaces. They go on to say that decrease in surface energy manifests the repulsion of water molecules over superhydrophobic surfaces, which leads to maintain fluid contact with smaller parts of the surface. So what does this mean in regular English? Well, first of all, by creating micro or nano structures on the surface, for example, ridges that are all aligned in the same way, these are very tiny ridges, it reduces the water's ability to touch the surface because in the troughs, the water cannot touch there. The water has a certain amount of flexibility to it, a certain amount of surface tension. So if you make these undulations and these peaks, the water can't actually mold to the surface very easily. They need to be very small, obviously, but these little grooves do that. Secondly, the low surface energy refers to the boundary layer. We know that the fluid very close to the wall is very slow moving. If you don't know about boundary layers, go to our YouTube channel and look at one of our videos called Area Fundamentals Number 1, Boundary Layers Explained. In it, we explain boundary layers and how they work. So this slow moving flow has trouble wetting this undulating surface. That, in a nutshell, is how hydrophobic surfaces work. So these researchers, they looked into how a 3D NACA 0012 airfoil at Reynolds number of 1000 is affected by the superhydrophobic surface. The authors say that this Reynolds number is chosen because it is roughly an average of what sea animals face. So sea animals, they experience Reynolds numbers between 0.01 all the way up to 1 billion. So it's a really big range. But these researchers said, okay, well, a lot of sea creatures around about 1000, so that's what we're taking. We're not taking like 0.01 or 1 billion. Let's take it at 1000. And the idea of this superhydrophobic surface comes from sea animals that swim. Many of them have this superhydrophobic skin. So to do this, these researchers are using CFD, which is probably the better of the two approaches for this particular study. The other potential approach is being experimental, obviously. The reason why CFD is better, generally speaking, for this research is because it is far easier to get the data without disturbing the flow. So if you were to go into your wind tunnel and do this experiment, or your water channel, I guess, trying to get boundary layer information experimentally is very difficult, especially if you don't want to alter the boundary layer. For CFD, on the other hand, you get the data and there's no problem there. You don't have to worry about altering the boundary layer because you're getting that data whether you like it or not. So the CFD domain is shown in figure 1. It is generally good. So this inlet is the C shape, which I really like. We've talked about that in other podcasts. This really helps reduce the time it takes to investigate other angles of attack. The wing is situated quite far from the top, bottom, and outlet. That's good. And the wing spans the entire length of the domain, the entire width, And the symmetry planes are used on the sides to create an infinite wing scenario. In other words, no wingtip vortex occurs. I'm not really impressed with their description of their CFD setup though. They miss a lot of important details. So when I was reading this, they missed things such as the termless model they used, the exact dimensions of this setup, and the time stepping. They use an unsteady CFD, but they don't tell us much about it. But let's move on to the information they do give us. So the first one, which is one of the most important parameters, is something called the gas fraction, which they talk about just here. So the gas fraction tells us how much of the surface is in contact with the water. A gas fraction of 0 means that all of the surface is, while a gas fraction of 1 means that none of the surface is in contact with the water and all of it is in contact with air, or the gas that is there. In this particular case, air. So this fraction is arguably the most important parameter in hydrophobic research in general. These researchers looked at a few different gas fractions to tell whether this affected the flow physics and the resulting forces. So this gas fraction really tells us how good the surface is at being hydrophobic. The higher this gas fraction, the more hydrophobic the surface is. These researchers also looked at this foil at different angles of attack, ranging from 0 to 25 degrees. And 25 degrees we start to get into very deep stall. So for this CFD, the validation process is also lacking. For example, in table 1, they have here, they showed validation data for the 2D wing against experimental data. But this is good, like the research, these numbers line up very well. But in this study, they're looking at 3D as well. Well, kind of 3D. It's not exactly 3D in the sense that there's a wingtip vortex, but it's 3D in the sense that there are 3 dimensions. So regardless, their 3D model doesn't seem to be validated here, only their 2D model. And sure, the 2D data lines up very nicely with literature, but that doesn't necessarily mean that the 3D model is good. We don't know that. One thing, and this is what I mentioned before with their CFD, there's something to be wanted here. There's some lacking information. One thing they do is the good independent study though. So one they have for a number of different cells in the domain, they don't do a great job. Not a bad job either, but not a great job. So in table 2 and table 3 here, we see that they are looking at 2 different finenesses for the grid. They have the coarse grid and the fine grid. The problem is that they only look at 2, not 3. So this coarse and fine and not medium. The good thing is that both meshes give the same lift and drag coefficients within reason. So you can say that the mesh has converged. You don't need to go to a finer mesh. The bad thing is that they didn't look at even coarser meshes. So with these meshes, they're using up to 16 million cells. But who knows? They might be able to get away with 10 million and be much quicker with their CFD and use fewer resources, but we don't know. So the grid independent study is okay in terms of, like, we know that it's accurate, that's their mesh, but we don't, they didn't use the most economical mesh possible. So with their entire CFD setup, I would probably rate it about a 6 out of 10. There are a few things that they need to do that they do well, but there are other things that they don't. Also, they don't include very important information about the CFD setup, which is how much we can trust the results, simply because we don't know. But let's move on to the results. So in figure 2, which is down here, in figure 2b in particular, we see the effects of the superhydrophobic surface on the lift coefficient for different gas fractions. So we have the gas fractions in this legend here ranging from 0.25, which means that 25% of the surface is in contact with gas or the air and 75% with the water, all the way up to a gas fraction of 0.9. So 90% of the surface is in contact with the air, 10% with water. So it is very obvious that as the gas fraction increases, the lift coefficient increases as well. We can see here that like the red line, these red dots are much lower than the green dots, and then the yellow dots are next, etc. So overall, a 20% gain is quite regularly seen when the gas fraction is only 25% and when it goes to 90%. So in other words, when only 25% of the surface is in contact with the air, 75% is in contact with the water, compared to 90% of the surface in contact with the air, compared to only 10% of the surface in contact with the water. As for the drag coefficient, figure 3b also shows some really good results. Increasing the gas fraction drops the drag coefficient, and some cases up to 60%. So you can see here at like 16 degrees, you have, for a gas fraction of 0.25, the drag coefficient is about 0.24 perhaps, 0.25. But for a gas fraction of 0.9, the drag coefficient is below 0.1. It's a massive reduction. So this is insane because for a NACA 0012 airfoil, if you have a flow control device that can reduce drag by 10%, that is amazing. If you have a flow control device that reduces it by 60%, that is phenomenal. You don't see that almost anywhere. So 60% drop in the drag coefficient while you get a 20% increase in the lift coefficient is incredible. So these two graphs show a lot of potential for superhydrophobic surfaces. As for the stall angle attack and the behavior from these graphs, there isn't too much to conclude. So you could say that they all stall fairly similarly, but let's look at figure 4, which has some more information about that. So figure 4 down here shows the lift coefficient with time for when the hydrofoils are at 10 degrees here, 15 degrees here, 20 degrees here, and 25 degrees here. And if you're just listening to this on our Spotify channel, you can watch the video on Spotify as well, and or our YouTube channel. So you can see what I'm pointing to here. Overall, I might conclude that the gas fraction slightly affects the stall. So for example, in figure 4a, which is for 10 degree angle attack, when the gas fraction is only 0.25, so this red line, this is the loss that the researchers looked at here, there is some slight wiggling in the lift coefficient, which indicates some level of stall. As angle attack increases to 15 degrees, there is a lot of wiggling about by the 3 lower gas fractions. And the lower the gas fraction, the more the coefficient wiggles about. So this pink line wiggles a lot compared to the yellow line, which wiggles only a little bit. So it indicates that potentially the low gas fraction foil has a lot more stall going on than the high gas fraction foil. In fact, for the gas fraction of 0.9, there isn't much wiggling at all. So we can say that pretty comfortably that the flow over this very high gas fraction foil is largely attached. So this might suggest that perhaps increasing the gas fraction delays stall a little bit. Now you might be thinking that when the gas fraction was 0.25 and the angle attack was 10 degrees, so this one here, this red line, that angle attack was too low for the foil to start stalling, but the Reynolds number is also very low too, it's only 1000. So this is very normal for a NACA 0012 to start stalling at around 10 degrees when the Reynolds number is so low. Similarly, in figure 5, let me scroll down to that here, we have the drag coefficient for 10 degrees, 15 degrees, 20 degrees, and 25 degrees. And this is for gas fractions from 0.25 up to 0.9. After seeing the lift coefficient results, the results here for the drag coefficient are expected. Again, at about 10 degrees, there is some slight wiggling about when the gas fraction is 0.25, so this red line here, which is consistent with the idea that the foil is starting to stall as well. So this means that the flow is stalling a little bit, separating, reattaching. That changes the pressure coefficient a little bit, and also the pressure drag, and that increases the drag and then reduces it periodically. That's why we get this stalling pattern here. And if you don't know about the different drag coefficients either, check out our playlist on aero fundamentals as well on our YouTube channel. We have some videos on that. Anyway, as the angle attack increases to 15 degrees, we can see in figure 5b, the 3 lower gas fractions result in varied drag coefficients as well, while the highest gas fraction of 0.9 is still very stable. It's very straight here. Then at higher angles of attack for figures 5c and 5d, which is for 20 degrees and 25 degree angle attacks respectively, the drag coefficient becomes very unstable, and you'd expect that because of the stall. There is so much stall going on that these drag coefficients just are all over the place. This figure also shows just how much the gas fraction affects the drag coefficient. So in figure 5a, a gas fraction of 0.25 yields a drag coefficient of about 0.155, while the gas fraction of 0.9 yields a drag coefficient of 0.095, 39% less at this angle of attack. It's really incredible. I'm very shocked at how much this hydrophobic surface affects the drag and lift even. So these are the forces. What about the flow physics? Let's move on to them because we see even more interesting results. So in figure 7, we see isocontours of the Z vorticity for the foils at 10 degrees, 13 degrees, and 15 degrees for gas fractions from 0 up to 0.75. In essence, this figure shows us how much vorticity is being created and shed from the foils. Again, if you don't know about vorticity, check out our video on YouTube called Air Fundamentals number 10, how to calculate vorticity from velocity field with example. We go through vorticity there. So this figure clearly shows that as the gas fraction increases, the amount of vorticity created and shedded drops dramatically. So at a gas fraction of 0, there is this periodic shedding of vorticity even at 10 degrees. But when we go to the gas fraction of 0.75, it's just this nice sheet. So there's not much vorticity going on there. There's not much of a breakdown going on there. It's far more well behaved. In fact, at 10 degrees, at this gas fraction of 0.75, there's almost no vorticity. Let's jump to figure 12 because that talks about the Strahl number, which goes very well with what we just covered here with the vorticity. We'll skip over some of this stuff. We'll come back to it later. But in figure 12, we have the Strahl number here versus the gas fraction for the angle of attack between 10 degrees and 25 degrees. So the Strahl number is a way of telling us how quickly vortices are being shed from an object. It's a way of comparing two objects with different shapes and even different velocities. A high or low Strahl number is not necessarily better or worse, but it gives information about the flow. For example, for the Strahl number of here, we can calculate the frequency of the vortex shedding from an object, and so we can determine if the vortex shedding will coincide with the resonant frequency or not before we even make the thing. That's pretty cool because if you make something and then the vortex shedding matches the resonant frequency of that thing, that leads to catastrophic failure. For example, there's a very famous video of something called Tacoma Bridge, and this is back in like the 1940s, and we've done a podcast on it, I think, where this bridge was like galloping. It was like literally moving like water. That's how much it was flexing, and then that just led to it breaking down because of the resonant frequency matched the frequency, the shedding frequency of the vortices matched the resonant frequency of the bridge. That led to catastrophic failure. So using the Strahl number, we can get good information about whether something will be safe or not before we even make the thing. That's really powerful. Anyway, figure 12 shows that the gas fraction greatly affects the Strahl number. We can see changes up to 30%. So for example, here for a gas fraction of 0 compared to 0.9, we get it's like 0.45 for the Strahl number compared to 0.48 maybe. So that's about 10% there, but it changes even more for this yellow line here. So what that means is that with a superhydrophobic surface, we can change the vortex shedding and move the frequency away from the resonant frequency and even change the frequencies of the noise being emitted. So noise often comes from vortices being shed, and the frequency that it's shed at is the frequency that we hear, the tone. So by changing that, we can either change it to broadband noise or shift it out of a frequency that we can hear, or even like change it to a frequency that isn't so annoying. So the superhydrophobic surface even changes that. Let's jump back to figure 9 now, and this figure shows the fast Fourier transform of the wakes for 3 different gas fractions here. So we have gas fraction 0, gas fraction 0.25, and gas fraction 0.5. So the fast Fourier transform is a way of decomposing the flow into its frequencies. You know how I just mentioned before with the Strahl number that it tells us the frequencies that a vortex is being shed at? Well, the fast Fourier transform helps us determine what those frequencies are as well. If you have that, just the general data, you can then just apply this and figure out what those frequencies are as well. So one more thing to point out is that the fast Fourier transforms also give the harmonics. So we can see here we have F1, that's like the basic frequency. Then we have 2 times F1, that's the harmonic. Then we'll have 3 times F1, and then etc. And we also have something called subharmonics. They're not that important here, it's just important to see this major frequency here for now. So the fast Fourier transform is very useful. It is also faster than the regular Fourier transform, and you better believe that it's faster than the slow Fourier transform. But anyway, in figure 9, we see that the gas fraction really affects the vortex shedding frequency as well. We can see that when the gas fraction is 0, so this top figure here, so the entire surface is also wetted. The vortex shedding frequency is just below 0.75 hertz. It's maybe about 0.7, this one here. But when the gas fraction is now 0.5, this one here, the vortices are shed at a frequency above 0.75 hertz. So you can see here it's like almost 0.8. So that's about a 10% change in the frequency. So from all this, we can see that a superhydrophobic surface greatly affects the flow physics and the forces of the foil. We saw in this research that it is highly beneficial for the forces, so it increases the lift coefficient, while reducing the drag, which is incredibly difficult to do. So both things are great. But this type of surface also helps when it comes to reducing vortex shedding and even preventing stall. It is such a great idea, and I really like this podcast. So if you did too, please hit the like button and subscribe and or follow, depending on which platform you are listening on. And if you want to get better at aerodynamic theory like we've gone through here, or CFD, check out our courses link in the description. So we went through the CFD before, we decomposed what was good about it, what was bad about it. In our course we do similar things, and we did talk about how to actually make your CFD really good and what you need to report for other researchers and people to trust your CFD, and what programs to use, etc. like that. And if you want to make your experiments 2 to 4% more accurate, get yourself an atmosphere hawk. It's instrument we make to accurately measure the density of air. The reason why this is important is because the density of air changes all the time. For example, if you come into your wind tunnel in the morning, then come back after lunch, the density of air is changed by a few percent in just those few hours. The density of air is affected by the temperature, pressure, and humidity. So having you even in your wind tunnel changes the density of air because you're pumping out heat and more water is going to the air from your breath and talking. What's more, the density of air changes even more than 2 to 4% between days, weeks, months, and seasons. So 10 to 15% changes are very normal, which means that you need to take them into account in your experiments. What's more, if you don't take them into account, then not only are most of the things you're finding in your experiments are just random error, but when you use your experiments to validate your CFD, it won't work, because one of the major reasons is that so many people have trouble validating the CFD is because their CFD density doesn't match the density of air in their experiments. It's not that the CFD is wrong, it's just that there's this difference, and so of course they're not going to line up. So get yourself an atmosphere hawk and you get rid of those errors in your experiments and CFD, and make your CFD more accurate in the validation process. As we went through here in this podcast, their CFD validation was lagging, I would put it nicely, I guess. So you can find the link to the description for the atmosphere hawk in the description, and I'll see you next podcast. Peace, amigos.